Hello and welcome to the brief demonstration of three-phase full wave bridge rectifier. Three-phase full wave is nothing but a three-phase fully controlled converter. You can see a simple bridge diagram. There are 6 thyristors and you can see a control, basically I would say not control, a load circuit given over here, and a freewheeling diode is also shown, which is connected across the output. So this is a simple block diagram for the given circuit. Now in this unit you can see on the back side we have connected basically a three-phase high voltage supply here. You can see a 4-wire supply, 440 volts supply, and which is connected to the back side of the unit. So you have to just follow the proper color code. RYB, neutral and earthing wire is also given. If the proper earthing is available in the college, you can connect that. And this is the mains on-off switch for this three-phase. So basically these are the this is the input side, and now you can see this is the control panel on the front. From operational point of view, it is very easy. Here a dedicated cable is provided, which you can connect to the load bank 1, which is, I can call it as a lamp load bank, and in the same load bank there is a provision to connect a L load also, that is the inductive load also, to form a RL load. So it is written here, if in the absence of a choke, you can put a link across these 2 points, so it will become a only purely R load. And so you have to short these two points when you want only R load. And when you want to connect a RL to form a RL load, basically you have to remove this link, and after removing this link, you have to connect a link from this point to the this is the choke, the load bank where the choke is kept inside, and the 2 terminals are given. So you have to remove the link across these 2 points, and instead of that, one wire will go to the one terminal of the choke, other wire will go to the other terminal of the choke. So L will become in series of the R, so it will become a RL load. So this is how you can configure the load as R or RL. Now when we connect a L, you can see the effect of freewheeling diode also. So we have provided a freewheeling diode also, and there is a switch to connect the freewheeling diode or disconnect the freewheeling diode. So there is a provision for that also. Now this is a dedicated 12-pin socket which goes to the load bank. Now here this is the indication for step down transformers. So I can say when these lights are glowing, all 3 transformers are okay, and I'm getting a output across these 3 terminals. So basically we are using a isolating and step down transformers. So if you connect a multimeter in AC across any of these line to line, you can get around 170 volts depending upon your incoming AC voltage. So this is an indication of incoming AC is working properly. Now this is the output side, I would say. This is the control side. Voltage control potentiometer is nothing but it controls the firing angle of the control circuit. I can switch off the firing circuit like this. When this switch is on the downward side, the firing circuit is on. Now in this same circuit we are providing 2 different configurations, as a full wave, which is a fully controlled converter, and a half wave. In a half wave mode we'll be having only 3 thyristors, so the output will be approximately half of what we are getting in a full wave mode. This is the fuse for the armature, or I would say fuse across the output. Then this is the test point for connecting the CRO. So you can see clearly it is written here, attenuated voltage output for CRO. So it is a attenuation is done already, 10 times attenuation is done. And these test points are directly high voltage test points. Of course they are isolated, but they are high voltage. So you are not supposed to short any of these test points, not these also. Because this will, if you short this, then the transformers will be shorted, and in any case if you short this, then the output will be shorted. So this is the main precaution any user has to take. Then this is the ammeter you can see, and this is the voltmeter. Now on this side you can see various test points are given for the firing circuit. So if anybody wants to study a firing circuit in deep also, this is more than sufficient, where this is the reference to the zero cross detector, then this is the output of the ZCD, and these are the 6 firing pulses for 6 thyristors. So you can study the relation between the ZCD and each pulse to the thyristor. Only the precaution, if you want to study at a time, if you want to study the ZCD with respect to the any of the firing pulse also, you can do it by connecting a CRO in 2 channels, or you can use the dual channel DSO or CRO, and the ground will be common for both the channels. But at any point of time, you should not connect the CRO at this terminal and at this terminal, because this is the firing circuit and this is the power circuit. So both the grounds are isolated. So you should not try to connect a CRO over here as well as over here. That is not recommended, and that will damage the equipment permanently. So that is the most important precaution. Now, being a three-phase fully controlled converter, we'll be getting a DC output. So as we have adjusted our step-down transformer voltage as around 170 volts, we'll be getting around 220 volts DC output maximum. So you can see that it is as simple as this. I am just varying the potentiometer over here, and I am getting a variable DC output over here from almost from 0 to 220 230 volts depending upon the line voltage. Now from students point of view, you can measure the line voltage, you can measure the output voltage, you can measure the DC current, then you can see the effect of R and RL load, then you can see the relation of ZCD and the firing pulses. There so many parameters can be studied, as well as you can study the output waveform of the three-phase fully controlled converter, as well as you can calculate the theoretical output versus experimental output found. So that calculation part is also given in the manual. Now the most important point is also that you can see right now we have followed the color code as R, Y, B and neutral. So at sometimes it may happen. Now at our place we have found out that this is the real R, which is coming from the your state electricity board, but it may happen that at your point the wireman might have randomly connected some terminal to the red terminal. So incoming line may not be R, but he has not seen the any phase angle relation or phase relation. So in case if you are not getting a proper control, you may have to change the phase sequence. You can see out of these three terminals there are at least 6 different possible combinations, and just you have to change at a time 2 terminals. Like I can swap yellow to red and red to yellow, like that. At a one time you have to just swap these two, and if it doesn't work then you swap Y and blue. Like that you have to change the sequence if required till you get a proper control. So that is also one of the important point. So if the proper sequence is not maintained, you may think that the equipment is giving some problem, but there is no problem with the equipment. It may have the problem with the incoming phase sequence. So that is one of the important point. Now, as I was telling you about this firing circuit, I am connecting a CRO across the output, and you can see this is the output waveform. Now, being a three-phase fully controlled converter, the proof is that my all 6 thyristors are working properly. Is I will put this in full wave mode, and I will just switch on the CRO. I have connected output across this TP11, and I have now just stopped my DSOs. DSO is in a stop mode, so I am just capturing that image, and I am scrolling that image. Now I can see that the difference, time difference between these two, any of 2 successive pulses is 3.3 milliseconds. It is 3.3 milliseconds. This is the one division is 2 milliseconds, and almost I would say 0.4. So it becomes a 3.3 milliseconds. The time between this pulse and this pulse, or this pulse and this pulse. So basically 3.3 into 6 is equal to 20 milliseconds. That becomes a 50 hertz. So this is a proof that my all 6 thyristors are firing, and this is nothing but a 3-phase fully controlled converter. So I will just put a run now, and you can see I am decreasing the firing angle. So basically you have to understand the relation. When the voltage is at lowest most point, the firing angle is the highest firing angle, and when I am increasing this potentiometer, actually I am decreasing the firing angle. I am going towards 0. So when I am getting the maximum voltage, my firing angle is almost at 0. So this is almost at 0 firing angle. So you can measure the firing angle also. Now only the limitation for measuring the firing angle in 3-phase fully controlled converter is, because there are 6 thyristors, every pulse is fired at 3.3 milliseconds, the DC ripple content will be more. So as I increase the voltage, output voltage, my DC line will be going away from the ground. So like this. So if you have a variable pure DC power supply also, you can see as you increase the voltage, the DC line will go up from the ground. The similar characteristics is shown in case of three-phase fully controlled converter. So because of that, it is difficult at the times to measure the firing angle just by looking at the relation of this line and ground. So for that, for simplicity, we have given a few diagrams in the manual. So you are expected to do like that. So if my diagram is saying this is 30 degrees, you adjust your waveform such that this image as well as which is shown in the manual's diagram is matching, and then you have to agree that that is the 30 degrees, and you take a alpha as a 30 degrees and then make the calculations given in the manual. So this is how you can calculate various values for the expected output and theoretical output, or the experimental output and theoretical output. So I think this is sufficient, and you can study various things in that. You can study the effect of L also. Now, right now the freewheeling diode is connected. I will just disconnect the freewheeling diode. So I put this in a normal mode, and this is the RL load. I will decrease the voltage. I will increase the firing angle. You can see it is conducting in a negative half cycle. So this is the characteristics of RL load only for higher firing angles. If I decrease the firing angle, if I increase the voltage, these characteristics won't be seen. Again, I have increased the firing angle, and now I am putting the freewheeling diode. So you can see as soon as I have connected the freewheeling diode, the negative part is blocked. So these are also an effect of freewheeling diode on the three-phase fully controlled converter's output. I think this is sufficient. Thank you.